Hello, now it's me again. Hopefully you will see 2018 Chemistry 11, the clip 002. Yes, last class we have started the Unit 1 classes, and we have looked at a few atomic what do we call atomic theory, and those atomic theory include from the beginning the Dalton one, and then we'll look at a couple of them in your work. I asked you to illustrate a couple of the atomic theories over the time, so hopefully you have done those exercises. If you haven't done it, just keep going, finish it. I would really like to you to send me your work. You have my email address. Please finish those questions that I sent you last week. Then yes, let's start this clip. Don't want to waste our time. Problems. So there would be a problem of a very famous models. We call them the Bohr models. If you still remember what we discussed, what I tried to explain it last time, the Bohr model is a pretty significant improvement of understanding atomic theory, and we talk about there would be electrons running at a constant energy level. We call those energy level shell. The one that closest to the nucleus, we call them the first shell. We generally call them n equals to 1. N equals to 1 means the lowest energy level. We always use energy level to describe what we shell. Shell equals to energy level. So when people say the first shell, the second shell, is exactly the same as the lowest energy level, then the second lowest energy level. When we try to explain Bohr model, it's pretty good for us to explain, okay, electrons has its own patterns. There will be a maximum numbers for each shell. When n equals to 1, according to the formula that we discussed with the electrons, is 2 times n to the power of 2. That makes the maximum numbers of the electrons holding in each energy levels. When n equals to 1, 2 times 1 square makes 2 electrons. So what does that mean is, in the very first shell means the smallest one next to the nucleus is very small. So the maximum that you can get is 2 electrons. When n is equals to 2, there would be different calculations. 2 times n square means 2 times 2 square. As you should know that 2 times 2 equals to 4, and 2 square is equal to 4. 2 times 2 square is 8. So when you have the second energy level, the maximum numbers of electrons it can accommodate would be 8 electrons. So and so on and so on and so on. You should have done this exercise. I'd like to see a little bit of your calculations later on. Then if you just look at Bohr models, which is nothing's wrong until we reach 20. So let's try to show you the Bohr models very quickly. I used a tables like this: n equals to 1, n equals to 2, and n equals to 3. The very first hydrogens, then we have helium, lithium, beryllium, boron, carbon, and all the way down, maybe we have neon and calcium. When is a hydrogen? According to the Bohr models, we can show them, show people about the electron configuration of hydrogens. All we need to do is put one there, because if you have a neutral hydrogen atoms, it's 1 protons, then 1 electrons to balance with each other. Then the next one is helium. Then we have 2 at the first shell. Then 2 and 1 for lithium. Beryllium is number 4, could be 2 and 2. Boron is 2 and 3. Carbon is 2 and 4. And all the way to neon. Neon is 10 elements. So it's 2 and 8. Because we know that during the calculation, the maximum number for the second shell, which is 8. So now we have one more. The one more electrons, it cannot go into the second one, it goes down to the third one. From the number 1 all the way to number 11, it works really, really well. And how about we keep going to look at until 18. So the second one, sodium, next to it is Mg, then we probably see some phosphorus, and then we have argon as 18. So for magnesium is number 12 would be 2, 8, and 2. So we have done all this previously, and you should be able to tell me phosphorus is number 15. So you have 2, 8, and 5, and number 18, we skip 16 and 17, then we reach argon. Argon is number 18, and we have 2, 8, and 8. So up to 18, we are very happy with it. How about 19? 19, you will be seeing some exceptions. So let's use different colors to look at that. Calcium, you would expect that because it's 2, 8, the third shell can get up to 80, get up to 2 times 3 square, which is 18. The maximum number for n equals to 3 is 18 electrons. So you would expect that should be 2, 8, and 9. And calcium would be 2, 8, and 10. However, according to Bohr models, that fit perfectly. But in observations, we realize both of them, they are not happening. It's not true. It's not doing something that Bohr model predicted. Instead of doing 2, 8, and 9 and 2, 8, and 10 for calcium, we find one thing. The actual electron configuration would be like this. It's 2, 8, 8, and 1. One of the electrons move to the fourth shell when n equals to 4, instead of start filling up the third one. For calcium, it's 2, 8, 8, and 2. And this, the red one that I'm just using, would be the correct electron configurations. For potassium and calcium. So you would ask me like, what would be the reason behind that calcium is not 2, 8, and 9, while calcium should be 2, 8, 8, and 1? It's all down to one rules. The rules that we have learned for many times. We call them octet rules. So what octet rules implied would be when you reach up to 8, it sort of like become pretty stable. When it become stable, you don't want to disturb them. Then and once it reach that, you want to try to keep it as stable, keep it as that as possible. And 288 compared with 289, then 289 doesn't belong to the octet rules. Then we will keep the 8 and kick out the 1 and move on. So let's try to look at potassium. Potassium is K. And the number of potassium is number 19 elements. So if you're looking at the electron configuration is 2, 8, 8, and 1. All the potassium ion that we find on the world, it is K positive. It means what is you have 19 protons as a positive contribution for the atoms. Then, because it's the neutral atoms, we would expect that it would have 19 electrons to neutralize it. So the charge for all the neutral atoms would be 0 at the top. We don't draw 0 because we expect that when you don't write it, it's 0. Then, when you try to form ions, octet rules apply. When the octet rules apply means that it really wants to become the octet. Octet means noble. is they want to become the electron configuration for the closest noble gas. The closest noble gas is argon, 18. So instead of 19 electrons, one of the electrons here is going to move away or being taken away. When you take away one electron from potassium atoms, then it becomes 19 positive and 18 negative. So if you can do a simple maths, 19 positive and 18 negative, you will have overall one charge. And K positive is what we call the potassium ion. And you never find the other one. So you will never see like potassium becomes K9 positive. If you're looking at that, that would be what Bohr model implied. Bohr model would be 2, 8, and 9. Then to become basically octet roots, we want to reach 2 and 8. So what we do, we're going to kick out all 9 electrons to become octets. And taking 1 electrons away or taking 9 electrons away, taking 9 electrons away is way too difficult. So none of these would happen. And in reality, we do find that all the cases for the potassium ion, instead of K9 positive, we would never see that. We only see K positive in the world. So now let's move on to look at a bit further. So what happened if you ask me about like what happened when you have 21? So up to 20 is 2, 8, 8, and 2. Then what happened when you have 21? And we find an interesting things happening again. For 21 is Sc, scandium. Number 11 is scandium, and we find the electron configuration would be 2, 8, 9, and 2. Somehow something really funny happened. Instead of 2, 8, 8, and we go back to the third shell. And the 22 is Ti in titanium is 2, 8, 10, 2. And 23 we have let's move on. Just skip a few. You know that you can go back to look at your periodic table for the rest of it. Let's skip a few all the way to 29. What is 29? 29 we have copper. Copper is 2, 8, 17, and 2. And we have the very last one, 30, that I want to discuss is the zinc. It's 2, 8, 18, and 2. So no matter what, for all of them, we find one thing in common. The n equals to 4 for the first 2 electrons. We observe there's one thing is the first 2 electrons of the 4th shell will need to be fielded before the 9th electrons of the 3rd shell. So it's very confusing. I know that because Bohr models make you confused. Then we will have a bit more discussion about all these different models. But you may remember one model that after Bohr suggested is called QM models. And these QM models will solve the problem that we encounter here. Bohr model would not be able to explain it. There's a limitation for Bohr models. However, we have a better models, which is the QM model, stand for quantum mechanic models. In quantum mechanic models, we can use it to explain everything that we find the movement of those electrons. Yes, QM models. but we don't. I'm not going to this. I'm not going to like put all the information in you today. The QM model will be take a bit longer to explain. So that's will come when I come back. I'll do some more explanation and do it with you. Yeah, QM models would be able to explain the observations above. But we will discuss this later when I'm back. Right, now before I move on to the next informations, one thing that you may ask, like, yeah, how do I be able to see the energies would be 1 plus, not 9 plus? There's one thing that we always use to explain the observation that we have. We call them ionization energies. And ionization energy is energies that you put into atoms and take away electrons. Ion means that you make them into ions. So anything, so let's say if you try to say, I always like to use sodium. So sodium is 2, 8, and 1. And what happened for ionization energy is the energies, if you want to steal things from atoms, you always need energies. Just something you can't avoid this. So you always need to put energies into it. There will be energy input. So the energy input, then you steal 1 electrons. It becomes 2 and 8. And that one becomes 1 positive. Yes? And you can always do a bit more further from Na positive, and you keep giving energy into it, so there would be another energy input. It becomes Na2 positive. When it's Na2 positive, you only have 2, 7. And everything you can keep go on and on and on becomes from 2 to 3 and 3 to 4 and 5 to 6. Let's say we have Na6 plus getting into Na7 plus. So when sodium losing 7 electrons, you only have 4 left. That would be 2 and 2. Ionization energies. So like why do we able to use ionization energy to explain the formation of ions? And it's quite easy to put them into a graph. Let's try to plot a graph, and it will be easier to explain to you. So if you look at your book should be able to explain to you a bit better if you search for ionization energies. For ionization energies, the Y is the energy input, so the input energies or ionization energies, and the x-axis would be just the number of electrons. So here would be the 1 and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons in sodium. So if you're going to plot the sodium ionization energy graph, for the very first one, it's extremely easy. The energy that you use is very low. Then, because like you're basically just achieving the octet rules, taking 1 electron out of 11, it becomes 2 and 8, and it's octet rules, and it's perfect, and everyone loves it. When it loves it, you just don't need to put energy, don't need to put as much as energies. But if you try to change 2.8 into 2.7, you're breaking the octet rules. You try to fight really hard, but like as long as you put enough energies, it will be like this. Then is a big jump. Then changing from 2.7 to 2.6 is not really hard because you're losing octet anyway. Then you'll find that the third one is not that hard. Then the next 7 would be pretty much steadily increase. 1, 2, 3, 4, 5, 6, 7. Then you'll find that, okay, approaching to the 4, 5, 6, 7. Here you reach to the point that you kind of going to the last 2 electrons, and the last 2 electrons right here is another octet. It's extremely hard to do that, have another big jump, and the last electron is not as hard. So you would be able to see there's like the first one, big jump, then very, very flat for the next 8, then another big jump, and becomes even flat again. By looking at these patterns, we can see this one would be the hardest to remove, and this one is another hard to remove. And that is telling us here would be the shell. So from the 3rd shell you get down to the 2nd shell, and the 2nd shell you start losing the octets. So every time you are having a big jump, you're losing octet from 8 down to 7, or then from 2 down to 1, right? Make sense? So hopefully you get a little bit ideas of the ionization energies. So one more time, I'm trying to explain that ionization energies means that it's the energy you try to put into the atoms and take away the electrons. Every time when you take away electrons, it becomes more positive. It should be getting harder and harder. But the gradually harder, it will reach to the point is to have a huge jump. And whenever you come into a huge jump, it means that you're losing the octet. So it's very easy to point out, like, what would that element be. So if I give you a particular ionization energy patterns, you can tell me straight away what would be that particular element. Because if you have the first 2 electrons, it's very easy to lose. Then the 3rd one is the big jump. Then it would be a 2+, and 3+ would be the first 3. Or you can just looking at that, if you're losing electrons with a big jump after 3 electrons, so it would be group 5. So things like that, you can kind of like put into your mind and try to remember it. And that is that ionization energy is quite important when we try to learn ion formations. So that's one thing. Just bear that in mind. Then another thing that I'd like to discuss today, except I'll move on from the next topics. Another next topic is this one, isotopes. So again, isotopes is important. That's why it's calling this again. But I'm not just talking about isotopes. I like to talk about isotope versus RAM. And what does RAM stand for? It's not the computer RAM that I'm talking about. It's not the memories. It is what we stand for, a relative atomic mass. Relative atomic mass is the number that you always find. It's the decimal numbers you always find in the periodic tables, and you use this a lot in the calculations. And we have to understand that and able to use it. In term 1 straight away. If you can't read relative atomic mass, you can't do any year 11 chemistry anymore. Then those 2 topics are highly related with one another. So first, try to think about what is isotopes. Do a little bit revisions for it. Carbon-12 and carbon-13. What's the difference between them? The differences between them is the nucleus. If you try to zoom in and look at the nucleus of carbon-12 and carbon-13, so we have to look at the nucleus. When you look at the nucleus, what can we find? There's only 2 types of subatomic particles we found in the nucleus. One is positive charge, protons. The other one is the neutral neutrons, particles. P stand for protons, Protons, and N stand for neutrons. So what is the number? How many protons can you find in carbons? No doubt 6 and 6. No matter it's carbon-12 or carbon-13, it has to be 6. The number of protons determine what type of the elements it would be. When you have 6 protons, it has to be carbon. It can't be something else. If you have 7 protons, it would be, what is 7? Carbon. And the one next to it is nitrogen. When you have 1 proton, means that it would be hydrogen. has to be they're equals. The number of protons determine the identity of the elements, and it's the identity numbers of it. So if you have your identity number, then that equals to you, right? And the funny thing is, the neutron is the thing that can vary even though you are the same elements. For carbon-12, you have 6. Carbon-12, the 12 means the mass of the nucleus. 6 plus 6 equals to 12. While 6 plus a number equals to 13, and that one has to be 7. You would be able to tell straight away the differences of different isotopes, carbon-12, carbon-13, is their number of neutrons, right? Let's give you a few more examples. How about hydrogen-1 and hydrogen-3, or oxygen-16 and oxygen-18? As hydrogen has to be 1 and 1 protons. So 1 plus 0 equals to 1, and 1 plus 2 equals to 3. Right? You have 2 neutrons and 1 proton for hydrogen-3. 16. The atomic number for oxygen is 8. So 8 then equals to 16. The other number has to be 8. And then 8 plus 10 equals to 18. So move this across up here. Easier to, I've got more room to write. So can you see the isotopes is just a same element with different number of neutrons that they found in their nucleus, right? Then what is the relationship between what's the point to look at isotopes and looking at the relative atomic mass? You'll find this here. Just give me a bit more room, not enough rooms to say. What is RAM? RAM is relative atomic mass, but in my terms, I always just say this. What is relative atomic mass? It's the average. If the average of what? If the average mass of all isotopes. So say hydrogen-1, hydrogen-2, hydrogen-3, and the relative atomic mass would be hydrogen-1 plus hydrogen-2 plus hydrogen-3, and take the average. So does that mean the relative mass of hydrogen equals to 2? It's not, because it also based on another thing, not just isotopes. It's also based on, it also depended on something called relative abundances. So relative abundances. So what is the relative abundances of Asian in the class? So you will very clearly say, okay, just how often you can see them naturally. How often you can see them naturally for carbon-12 and carbon-13? 99% of carbon is carbon-12. There's less than 1% that you can find is carbon-13. So the most of the carbon is carbon-12. And you will, when you take the average of it, we have to pay attention for those relative abundances. So when you try to do, there's a few assumptions. Yep, there's assumption that I'd like you to realize. There's some that you assume. One thing that is, not all isotopes have the same relative abundance. They're not 50-50 or just spread them evenly. Some of them would be definitely more than the others. Abundances. Then, so naturally, as I mentioned before, carbon-13 is like 99% compared to less than 1%. And if you try to compare CO35 and CO37, it's not that different, but still more. So roughly 3/4 compared with 1/4. So it varies. It doesn't. It has no reason at all. It's just what we find in the world. We couldn't find the reason yet. So if you can find a reason, you may be very close to the Nobel Prize in the future. Then for staying so long. So how do we calculate it? And we always use this particular formula. The formula is the relative atomic mass can be calculated by the percentage times by the isotope mass, and then plus the percentage times by another isotopes. Then you just keep going on and on. If you have 10 isotopes, just add all 10 of them with the percentage. Because this in percentage, if you divide it by 100, it gives you a better number, a whole number. It would be the relative atomic mass formula, right? So let's give you this one before we finish the class. Give you one example. So what would be this example? Chlorine 35 with 37. As I mentioned before, 35 is about 75% and 37 is about 25%. And so quickly, what would be the formula? The formula is the percentage times by the mass, and this percentage times by this mass. So relative atomic mass for chlorine would be 35 times by 75 bracket plus 37 times by 25. But the number would be too big, divided by 100. Then we will get the answer. So let's do it, the calculation straight away. The calculation would be 35 times by 75 equals to that, plus I couldn't do, just try to do the scientific with a plus a open bracket, 25 times by 37 closes. So you can try to do that with me at the same time. Altogether is 3,550. But remember, we need to divide it by 100 for getting the answer. Divided by 100, we have 35.5. So let's go back to 35.5. If this is 35.5, and we have what we call the relative atomic mass, and this is the mass that you find in the periodic tables, and it tells you one thing, just the average, and it's the average of the mass of all the isotopes, right? So try to draw a diagram to kind of make sense of this formula. So let's say you have 100 grams of chlorine gas, or whatever, chlorine atoms. So if you be able to collect all the chlorine atoms in there, and you will realize 75% inside there would be your chlorine 35, and then you will have 1/4, means like 25%, is 37. And what you try to do for this relative atomic mass is trying to take 1/4 times by 37 plus 3/4 times by 35. And then you plus them together and you reach the average. And the average would be 35.5. Right? And 35.5 means what? It means that it's the average of each chlorine atoms. And the average mass is roughly weight 35.5. So you're asked like, 35.5, what would be the unit? We cannot use gram to represent atoms because such is so small, and we have a particular unit called AMU to measure them. We call them atomic mass unit, which is equals to 1 protons. Right? It's like 35.5 protons for each. Take the average for each chlorine atom is like 35.5 protons in there. Is AMU. Right, so I think that is enough for this class. Make sure that you start working on your 10 questions now, and you should be able to hand it to me by Friday next week. Next week Friday would be checking the time. Today is the 9th. The 9th of Feb. Right, thank you for your attention, and I'll see you soon. Bye bye. About 35 minutes.